In today's session, we will discuss some of the most important and frequently asked questions on the BJT and associated circuits like biasing techniques, common emitter, common base configurations, and amplifier analysis. All these question models are based on the previous year examinations of GATE, IES, ISRO, DRDO, Polytechnic Lecturers, and other state public sector unit examinations. Let's welcome to the channel Electronics Pariksha. Next question. The voltage gain of CE amplifier circuit can be approximated for an ideal input AC source and is given by. So he's basically asking the voltage gain. If you see the previous videos, we have derived very clearly the voltage gain of a CE amplifier. Anyway, we'll try to see here also. Okay. So this is the basic circuit, CE amplifier circuit. This is R1 resistor and this is R2 resistor. And here we have got transistor, emitter resistor, and there is a emitter capacitor CE, collector resistance, output capacitor, and then comes load resistance. Here at the input side, we have got input capacitor Cin and input voltage source. Okay, this is the circuit of CE amplifier. But to calculate the gain, we have to consider the AC line circuit. So we need to consider AC equivalent circuit. AC equivalent circuit. Because we have to calculate the gain for AC signal. So for AC equivalent circuit, the DC sources should be represented with ground. And capacitors which allow AC and block DC. Capacitors block DC and allow AC. Only AC will be there through capacitor. So capacitors will act like a short circuit for AC. Short circuit for AC signals. So if you redraw the same diagram with these conditions, you will get the diagram like this. Both R1 and R2 will come in parallel with each other. And then comes the transistor. There will not be any emitter resistance here because the CE is there. The emitter capacitor will be replaced with short circuit. So this emitter resistance is bypassed. And here the collector resistance and the load resistance will be parallel with each other. And here we have got the input signal. Okay, this is basically the diagram, and the IB current flows like this and IC current flows here. So now if you calculate the output voltage is nothing but output current, collector current multiplied by output load resistance. Effective load resistance we have to take because the collector current flows through collector resistance RC and RL. Both are in parallel. So effective load resistance RL dash is nothing but RC parallel with RL. This is the output voltage. Then what is the input voltage? Here, if you see, if we consider from this particular point, without considering R1 and R2. R1 and R2 also will be there. But if we consider from this particular point onwards, IB is flowing through the base and emitter. If you take the loop like this, IB is flowing through the base and emitter. This base emitter junction will have a small resistance. That resistance is called emitter model resistance. Okay, there will be a small resistance. Emitter will have a slight small resistance, that is emitter model resistance, through which IE is flowing, emitter current is flowing. Okay, now if you take that particular equation, input voltage is nothing but IB into R pi. R pi is the resistance that is appearing here. Or you can take like this also, IE, the emitter current that is flowing through RE dash. This is the input voltage. Okay. So now, if you substitute this in the voltage gain, the voltage gain is nothing but output voltage by input voltage. Output voltage is IC parallel with RC and RL multiplied by IE RE dash. The IC, collector current and emitter current, will be approximately equal. So you can remove this 2 both will get cancelled, and AV becomes RC parallel with RL divided by RE dash, emitter model resistance. So here the answer is option D. Sorry, option C. RC parallel with RL, not RC into RL. This is not the answer. Option C is the answer. This question is asked in a previous IES examination, IES 2020. Very important model. If you see the next question, if the TA, ambient temperature of the junction, is 50 degrees centigrade, and if the junction temperature rises to 200 degrees centigrade, the junction temperature constant is 100 degrees centigrade per watt. The power of the transistor 2N1701 can safely dissipate in the free air will be. So here we have the formula. Theta is equals to the junction temperature minus junction ambient temperature. Junction temperature minus ambient temperature divided by power dissipation. If you substitute the values, we'll get PD is equals to Tj minus Ta divided by theta Ja. This is 200. Junction temperature has increased to 200 degrees. Ambient temperature is 50 degrees divided by 1000 degrees centigrade. So here the answer is 1.5 watts. Option B. Next question. Consider the following circuit configurations: common emitter, common base, emitter follower using a Darlington pair amplifier. The correct sequence is the increasing order of the resistances, input resistances. So if you see, for common emitter, this is the common emitter. Input voltage is applied here, and there is no emitter resistance. I am taking emitter resistance is in parallel with emitter capacitor. So I am replacing this emitter resistance with a short circuit. Okay, this is the normal diagram. Now if you see the input resistance is nothing but input voltage divided by input current, IB. If you come here, there will be a small emitter model resistance. I have already told you just before. This resistance is emitter model resistance, which is inevitable. So IA is the current flowing through it. So if you apply Kirchhoff voltage law here, V input is equals to IE RE dash. V input is equals to, this IA can be written as beta plus 1 IB. Beta plus 1 IB RE dash. So now the input impedance is equals to input voltage divided by input current, that is base current, is equals to beta plus 1 RE dash. So this is the input impedance of common emitter amplifier. Now we'll see for common base. For common base, input is emitter, output is collector, input voltage is given at the emitter side, and there is a current flowing, that is emitter current here. If you apply the Kirchhoff voltage law in this loop, the input voltage is equals to IE into RE dash, emitter model resistance. So input voltage divided by input current is equals to RE dash. This is the input resistance for common base. Similarly for emitter follower, that is nothing but common collector. We'll see for common collector. Like the video, share the video, and subscribe to the channel for better content and more videos. So input is the base, output is the emitter itself. So output is taken across the emitter. We cannot keep the emitter as short circuit. We have to place RE, emitter resistance. So here, how many resistances do we have? Here we'll have two resistances. One is a small emitter model resistance, and another one is emitter resistance. So both will be there. So output is collected across the emitter resistance. So here the input current is IB, output current is IE. So if you calculate this, for this, the input resistance will be input voltage divided by input current, which will be equal to beta plus 1 RE dash plus capital RE. This is the input resistance of emitter follower, that is common collector amplifier. This is for emitter follower. Now last comes Darlington pair amplifier. Now let's see Darlington pair amplifier. In the Darlington pair amplifier, we have got two common collector amplifiers connected back to back. This is the first common collector amplifier where input voltage is VB1, the input current is IB1. Input current is IB1. And this output is emitter, which is given to the base of another transistor. Collector is connected to common VCC. Output is taken across this emitter. Okay, here output is taken. So now if you see this, if you apply the same model again, here the current will be beta plus 1. Beta 1 plus 1 IB1. Here the current will be beta 1 plus 1 into beta 2 plus 1 into IB1. Okay. This is the IE emitter current 1, which is the input of second transistor. Again it gets amplified. So output will be beta 1 plus 1 into beta 2 plus 1 into IB1. So if you calculate the input resistance, it will be approximately, input resistance is beta 1 plus 1 into beta 2 plus 1 into IB into RE dash emitter model resistance. Okay. So if you approximate this beta 1 plus 1, beta 2 plus 1 to beta, and if both transistors have same beta value, then it will be beta square RE dash. So if you compare these values, the input resistances of common base amplifier is the least. Ascending order he told. So the least input impedance is common base amplifier. First comes common base. Second comes common emitter. Third comes common collector, that is emitter follower. And last, the highest input impedance is for Darlington pair amplifier, which is fourth. So answer is option D. This is very important question asked in the previous vice principal RPS examination. We'll see the next question. The transistor switch as shown in the figure has beta is equals to 120, VC saturation is 0.2, RC is 1.2 kilo ohms, and VC is 5 volts. So now the output voltage when transistor switch is closed, he has mentioned it as closed, and the minimum base current needed to close the switch. Here he told to close the switch. Means what does it mean? Switch is in, the transistor is in operating in saturation region. Transistor is operating in saturation region. Okay. So here, when the transistor is in saturation region, if you take the output loop KVL and input loop KVL, two KVLs you have to take. But here, he is asking for the minimum base current also. Okay, we shall take the KVL at the output side. Apply KVL at the output loop. What you will get, VCC is equals to IC into RC minus VCE saturation. So VCC is given as 5 volts. The collector current is not known. Collector resistance is 1.2 kilo ohms. VC saturation is 0.2. So from this, the collector current IC can be given as 4 milliamps. So we have got the collector current, IC saturation. Now we need to calculate the minimum base current. The minimum base current, IB saturation, can be given as IC saturation divided by beta. So IB saturation is equals to 4 milliamps divided by beta is 120. So it will be approximately 33.33 microamperes. It is the minimum base current that is required for the transistor to drive into saturation. What is the output voltage? The output voltage is nothing but VC saturation, which is equals to 0.2 volts. So the answer is option C. Next question. A transistor used potential divider method of biasing. R1 is 50 kilo ohms, R2 is 10 kilo ohms, RE is 1 kilo ohm. If VCC is equals to 12 volts and VB is 0.1 volts, then IC is, collector current is, he is asking. Very simple. First we'll draw the circuit. This is R1. The emitter resistance and collector resistance. VCC is given as 12 volts. R1 is given as 50 kilo ohms. R2 as 10 kilo ohms. Emitter resistance is 1 kilo ohm, and collector resistance is not given here. Fine. Now we need to calculate the collector current. So first, if you see, we need to find out the voltage here, VB. What is VB? VB is nothing but VCC divided by R1 plus R2 into R2, because the current flows in this direction. We will neglect the current, the base current, because base current will be nano amperes, microamperes. It will be very, very less. So neglect that current and consider this current flow. Current I1 is flowing through R1 and R2, and calculate it. Now VB will be 12 divided by 60 kilo ohms multiplied by 10. So it comes around 2 volts, right? So the voltage across this is 2 volts. And he has given very clearly VBE is 0.1 volt. Here, the voltage across the base emitter junction is 0.1 volt. So consider only that particular thing and apply input KVL here. If you apply input KVL, VB is equals to VBE plus VE, emitter voltage resistance. So VB is 2 volts, VBE is 0.1 volt plus emitter resistance is emitter voltage is emitter resistance multiplied by emitter current. So the emitter current will be 1.9 milliamps, which can be approximated to collector current also. Okay, emitter current and collector current both will be same approximately. So the answer is option C. This is one method of solving the question. There is one more method. I will just tell you one more method. Here what we have to do is you have to find out the VThevenins. VB itself is the VThevenins. VB itself acts like a VThevenins, which is equals to 2 volts. And you have to redraw the circuit like this. VThevenins and RThevenins is nothing but R1 parallel with R2. That particular value will be 25 by 3 kilo ohm. And then you give for the transistor, collector resistance RC, VCC, and emitter resistance 1 kilo ohm. Now you apply the input loop. Here also you will get the same thing. VThevenins is equals to IB base current parallel with R1 parallel with R2 plus VBE plus VE. So even if you solve this, you will get the same answer. VThevenins will be 2 volts. IB multiplied with 25 by 3 kilo ohm, and this is 0.1 volts plus IE, which is IB plus IC, both IB plus IC, multiplied by 1 kilo ohm. 1 kilo ohm. Okay. So if you solve this entire thing, you will get 1.9 is equals to IB 25 by 3 kilo ohms plus 1 kilo ohm plus IC 1 kilo ohm. So we need to neglect IB because it is very, very small, and IC is equals to 1.9 milliamps. So there are two ways to solve this problem. This is the first method. This is the second method. Okay. Let's see the question. A transistor circuit is shown in the figure. Assuming beta is equals to 100. Beta value is 100. Base resistance is 200 kilo ohms. Collector resistance is 1 kilo ohm. VCC is 15 volts. He has given VBA saturation is 0.7 and VC saturation is 0.2. VBA active is 0.7, VBA saturation is 0.8. Fine. Now the transistor is operating in which region? Okay. Now to find out to find out the region of operation, whether it is active region or saturation region, we need to do two steps. Step one is this is step one. Sorry. First step is to find the collector current, find IC, normal collector current. What is the normal collector current? You have to find out. Step two is you have to find out IC saturation. What is the collector current at saturation level? You have to find out the normal collector current. You have to find out IC saturation. If the normal collector current value, if normal collector current value is greater than IC saturation, then transistor is said to be working in saturation mode. If the normal collector current that is flowing in the circuit is less than IC saturation, then the transistor is said to be working in active region. Okay? If the collector current that is flowing is greater than saturation current, it is in saturation mode. If the collector current that is flowing is less than saturation current, then it is said to be in active region. Now let's find out. Step one. So how to find out the collector current? We know that by applying the Kirchhoff voltage law, we can find out. First, here, apply the Kirchhoff voltage law in the input loop. By KVL in input loop, you can write VCC is equals to IBRB plus VBE active. We have to take active value 0.7. Substituting the values. We do not know the value of IB. The base resistance value is 200 kilo ohm. And base emitter active, we have to take active value, that is 0.7. So VCC value is 15 volts. I am putting 15 here. With this, I can get base current IB as 71.5 microamperes. This is the base current I got. So what is the collector current? The collector current is nothing but this is a common emitter configuration. So we have the formula beta is equals to IC by IB. Using this formula, the collector current IC is equals to beta IB. So the beta value is 100 and base current is 71.5 microamperes. So the collector current we got is 7.15 milliamps. This is the collector current that is flowing in the circuit. Now we need to find out IC saturation. So for the saturation current, we have the formula. You have to apply KVL in the output loop. Apply KVL in the output loop. So by KVL at output loop, you will get VCC is equals to ICRC plus VCE saturation, because we are calculating the saturation current. So VCE saturation we have to put. So here IC saturation is equals to VCC minus VCE saturation divided by RC. So IC saturation is equals to VCC is 15 volts. VCE saturation is given as 0.2 volts divided by RC, collector resistance is 1 kilo ohm. So by substituting this, I'll get IC saturation as 14.8 milliamps. 14.8 milliamps is the current that is required for transistor to enter the saturation region. But present, the current flowing is 7.15 milliamps only. So transistor is working in active region. So answer is option C. The transistor is working in normal active region. Option C. We'll see the next question. Like the video, share the video, and subscribe to the channel for better content and more videos. The value of HFE, that is beta. HFE means the forward current gain, that is beta, of a common emitter configuration of a bipolar junction transistor is 250. So it's telling beta is equals to 250, which is nothing but the forward current gain of common emitter configuration, HFE. What is the value of alpha DC, ratio of collector current to emitter current for this BJT? This is very simple. Alpha is nothing but IC by IE. Beta is nothing but IC, collector current by base current. We have already seen the relationship between alpha and beta in the previous videos also. Beta can be given as alpha divided by 1 minus alpha. Or alpha can also be written as beta divided by 1 plus beta. So he is asking for alpha. So beta value is given 250 divided by 250 plus 1. That is 1 plus 250, which is equals to 0.996. So answer is option D. We'll see the next question. Assuming VCE saturation is 0.3 volts for the silicon transistor at ambient temperature of 25 degrees centigrade. HFE, that is beta, is equals to 50. So minimum base current required to drive this transistor into saturation for the circuit is. So the question is very direct here. This is the circuit we have to draw. This is a common emitter configuration. Collector resistance is given as 1 kilo ohm. This diagram is given in the question itself. This is the base current IB. VCC is plus 5 volts. Okay. This question is asked in IES 2016. Very, very important question. So he is directly asking what is the minimum base current that is required. IB saturation that is required to drive the transistor into saturation. So let's take the saturation formulas only. First, we'll calculate it. If you apply the Kirchhoff voltage law in the output loop by applying KVL in output loop, we'll get the formula VCC is equals to ICRC plus VCE saturation. This is our formula. So now VCC is 5 volts. Substituting these values, collector current is not known. Collector resistance is 1 kilo ohm. VC saturation is given as 0.3 in the question itself. So from this, I will get IC saturation current is equals to 4.7 milliamps. So this is the IC saturation, minimum collector current that is required to drive the transistor into saturation. Now we have to calculate IB saturation, which is nothing but here we have beta is equals to IC by IB. Using this formula, IB is equals to IC saturation divided by beta. That is 4.7 milliamps divided by 50. So IB saturation is equals to 94 microamperes. So this is the answer. So this is the minimum base current that is required to drive the transistor into saturation. The minimum collector current is this one. So we have to be very careful while solving these questions. Here the simple thing is VCE saturation. If you are substituting VCE saturation, you will get the saturation current, collector saturation current value. Okay. So be careful while solving this type of questions in the examination. This question is asked in IES 2016. Very important. We'll see the next question. In case of a small BJT model with common emitter, the collector current IC is 1.3 milliamps. When the collector emitter voltage VC is 2.6 volts, the output conductance of the circuit is. See here, conductance is nothing but the reciprocal of resistance. He is asking us to calculate output conductance. So here the output conductance for a transistor, common emitter transistor, is output current, that is collector current, divided by output voltage, that is VC. So substituting those values, 1.3 milliamperes divided by 2.6 volts, you will get output conductance 0.5 millimos. So answer is option D. This question is asked in IES 2017. We'll see the next question. An amplifier has a signal input voltage VI of 0.25 volts and draws 1 milliamps current. If the amplifier delivers 8 volts to the load of 10 milliamps, the power gain is, it's very simple. The power gain is nothing but output power delivered to the load divided by input power produced by the source. So output power is nothing but output voltage divided by output current, input voltage divided by input current. Now here the output voltage is 8 volts, output current is 10 milliamps. Input voltage is 0.25 volts and input current is 1 milliamp. So the power gain is, if you calculate it, it will be around 320. So answer is option B. Next question. The leakage current approximately doubles for every 10 degrees rise in temperature of the silicon transistor. If a transistor has IC P0 as 1000 nanoamperes at 30 degrees, what is the leakage current at 90 degrees? So we have seen this formula also in the previous videos. The leakage current IC2, that is the leakage current at new temperature, is equals to IC0 1 into 2 to the power of T2 minus T1, that is temperature. Second, T2 minus T1. T2 is 90 degrees, T1 is present temperature, current temperature, divided by 10. So IC02 is equals to, what is the current, leakage current? 1000 nanoamperes. 1000 nanoamperes into 2 to the power of T2, that is 90 degrees, minus present temperature is 30 degrees, divided by 10. Here 10 to the power of minus 6 into 2 to the power of 6. So it is 64 microamperes. Answer is option B. Sri Raghava Academy online coaching center for the regular and backlog students dedicated to diploma and engineering courses. Semester wise and subject wise coaching is available. Contact the number 70192 46753.